Hi everyone, welcome to the first lesson of Unit 4 of Grade 10 Math. So we're going to, this is just an introductory lesson to this, to something called quadratic relations. And the interesting thing is that this is really what we're going to be doing for the rest of the year. So for the next 2 months, we're going to be working with these functions and called quadratics and doing all sorts of different things with them, and we're going to become experts in these. The other name often used for quadratics are parabolas. So spelled like this, parabolas. And really what they are is they are functions that are shaped like this curve, like this U. And they can be upside down as well. So they can be like this, and they don't have to actually all start at the origin. They could, start over here somewhere. So we're going to learn all about these things called parabolas for 2 months, and you guys are going to become experts in them. All right, well, let's take a step back. Let's take a step back because I taught you all grade 9 math, and let's take a look at something called linear relations. And linear relations are basically lines. That's what a lot of the grade 9 math course was all about. And so we did a lot of work with lines. And so we got used to seeing what tables of values of lines looked like. And a typical example of a table of value might be something like this, where we'd have, the x values were 1, 2, 3, and maybe the y values were 1, 3, 1, 3, 5, and 7. So that would have been a typical example from grade 9. And we would have looked at this, and we would have said, I'm pretty confident that it's linear because we would have looked at what we called the first differences. And so I'm just going to write it here in red. We would have done something like this, and we would have said the first differences. And we would have said, well, what's the difference between 3 and 1? As you go from 1 to 3, it's a +2. And as you go from 3 to 5, it's a +2. And from 5 to 7, it's a +2. And we just verified that all the x's were changing by the same amount, and they are. They all go up by 1. And because it had constant first differences, we would have said, hey, I'm pretty comfortable that that's a linear relation. The other thing we could have looked at it was graphically, and what we would look for in terms of a linear relation is we'd look for straight lines. And so we'd look for something like this, so a straight line on a graph. Now it doesn't have to be like that. It could, a linear relation could be horizontal. Oops, I think I just moved that one off of horizontal. Let me fix that. It could be horizontal. A linear relation could be vertical. It could be sloping negatively. So there's all sorts of linear relations, but we'd look for straight lines. And then finally, I taught you last year that algebraically, you look for, you would look for something like this. You'd look for y is equal to 2x plus 1. And what you'd look for is no exponents on your x or y, on the x or the y. Or I should be careful because no exponents technically means 1. And so they both have an exponent of 1. Okay, something like that. We often don't show the 1 though. In fact, we rarely show the 1. So it would look something like this. So this, hopefully you guys would have judged that last year. Yeah, that's a line. That's a linear relation. There's no exponents. Well, last year we didn't really care about the other ones, but there are, for instance, if we had something, a table of values like this, where it had been 0, 1, 2, 3, so that's looking good. And let's say we, instead of, for y, we had values like this, 0, 1, 4, and 9. And so we would have looked at that last year, and we would have calculated our first differences, and we said, well, it's going up by +1 there, and there it's going up by +3, and there it's going up by 5. And so we would have looked at that and said, you know, those are the first differences, and we would have said, no, that's not a linear relation, and we would have been happy and done with it at that point. But what we're going to see now in grade 10 is that we can start looking a little bit beyond that, and we can do something that's called a second difference. A second difference. And so now we're interested in the differences in the differences. So the differences here. So what's happening between the first differences? Well, as they go from 1 to 3, that the second difference is that it increases by 2. And as it goes from 3 to 5, it increases by 2. And so we're going to see that quadratic relations have a constant first difference. Constant first difference. Or sorry, constant, my apologies, constant second difference. And so that's going to be interesting. Okay, graphically, what quadratic relations look like is they look like these U's, and they're going to be, they go up like this, and so they go up on both sides of the y-axis. So there's a, you know, there's a U. And again, last year we would have looked at that and said, well, you know, it's not straight, so therefore it's not linear. But now we're going to have to start recognizing that they might be quadratics. Now, quadratics could also point down, and they don't always have to start at the origin, like I said earlier. So it could be something like this. Okay, so there's another one, and it doesn't have to be, it could be wide like that, or it could be really narrow. This is also a quadratic. That's a type of parabola as well. So they can be wide, they can be narrow, they can point up, and they can point down. So those are examples of quadratics or parabolas. And finally, algebraically, the equations. We're going to be looking for things like this. Y is equal to x squared. So now we're going to see that the x's can have this exponent 2. Now again, this is a very simple quadratic, y equals x squared, but they can, you know, it could be something like this, x squared plus 2x plus 1. And here what we're going to see is the highest, as long as the highest degree is 2, it's still a parabola. And so now notice that the squared, the exponent 2 has to be on the x, not on the y. And again, you can have other terms, but as long as the highest degree is what we call it, is 2, in other words, the highest exponent is 2, it's still going to be a parabola. Now, there are parabolas in real life everywhere. You know, I just wanted to bring up some pictures here. You can see that there's some great architectural sculptures that are designed as parabolas. Here, this fountain, it's really cool. The fountain, as the water is shot up into the air, it follows a parabola, you know, and it's an upside down one. In fact, and I'll go to this one next, this basketball. Everything that's thrown into the air that is not, you know, doesn't have a way of propelling itself. So a basketball, once it leaves your hand, doesn't have an engine on it. And so basically everything thrown in the air follows a parabola. Anything that you throw, a football, a basketball, anything like that follows a parabola. Okay, so that's kind of interesting. This one I thought was cool. A banana, the shape of a banana is a quadratic function. And then I thought this one was interesting. My favorite restaurant, McDonald's, the golden arches. Now, interestingly, again, the parabola doesn't repeat itself, and so only one of the arches would be a parabola. So just be careful that if you start to see something like this, that is not a parabola. That's a different type of function. It's called a trig function. So that would be either a sine or a cos function. So remember that a parabola only has the one bend in it. It only has the one bend. Okay, well, normally what I would do in class is we do a couple little experiments to collect data on you know, where the data would represent a quadratic. And so let's just do this one together really quickly. And it says Theo is designing an apartment building in a pyramid design. Each apartment is a square. He wants to know how many apartments can be built in this design as the number of apartments on the ground floor increases. So normally I give out cubes in class and I get people to start building these. And so here it is. So obviously, if it's going to be this pyramid design, you could see that it starts and you'd have, in this first example, you just have one apartment. Here you could have 3 on the bottom and 1 on top, so there would be 4 apartments. Here there'd be 5 apartments on the base, and then 3, and then 1. And then I would ask students to build the next one, build the next model in the sequence. So I've done it for you here, and that's what it would look like. So this is the first model, the second model, the third model, and the fourth model right here. So we've got 4 different models of apartments. Okay, so then what we would do is we would build a table of values. So let's go to the next page. And this is what the table of values would look like. So, so the number of cubes in the bottom row is going to be our x value, and the total number of cubes, or the number of apartments, is our y value. So if you had 0 cubes in the bottom row, you would obviously have 0 apartments or 0 cubes. And now what about if we put 1 cube in the bottom row? Well, that was the first one that we really built. And then we'd have a total number of, we'd only have 1 cube. Did you notice that when we had 3 cubes in the bottom row, we had a total of 4 cubes or 4 apartments overall? That's this second one here that we drew. Okay. Now the third one, we had 5 cubes in the bottom row, and that gave us a total of 9. If I add those up, look at this. In that one where I had 5 on the bottom, I had 5, 6, 7, 8, 9. I'll show you here. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so that's why we have 9 in total. The next one, we placed 7 cubes in the bottom row, and when we add those all up, you end up getting 16. And I'll do one more for you. If we were to do another one, we'd have 9 in the bottom row, and we 25 in 25 total. So we'd have 25 total. Okay. So let's calculate the first differences. So these are the differences in the y values. I'll just show you here. It's the delta y. It's the differences in the y. So you could say to yourself, well, how did you go from 0 to 1? Well, you added 1. Or another way of thinking about it is you just take this value and subtract this value. So 1 minus 0. You can get the delta y either way. So here, how did I go from 1 to 4, or it's 4 minus 1? Well, that's 3. 9 minus 4 is 5. 16 minus 9 is 7. And 25 minus 16 is 9. So obviously we'd look at that and say, well, it's not linear. But let's do this second difference now, the second difference. And so again, how much I went, going from 1 to 3, that was a plus 2. From 3 to 5, it was 2. From 5 to 7, it was 2. And from 7 to 9, it was 2. So right away, we see that we've got constant second differences. And that is telling us that we're dealing with a quadratic. We're dealing with a quadratic. Okay. Well, let's graph it and see what this looks like. So again, in order to graph, I've got to go back to my first 2 columns. The graph doesn't care about first or second differences. It cares about the first 2. So here we go. Let's graph this. So I'd put a dot at 0, 0 right there. And then I'd go to over 1, up 1. I'm going to put a dot right there. Over 3, so 1, 2, 3, and up 4. 1, 2, 3, 4, so it's right there. over 5 and up 9. So 5 and all the way up here to 9. I think I could fit one more on there. 7. And I'm going to go up to 16. So 7 all the way up to 16 is right there. I won't fit that last one on. But you can see what we're getting here is that we're getting this curved line. It's curving up and it's getting steeper and steeper and steeper. Now we don't have any negative values to do here. And so we'll just leave it as the half parabola. But you can see that if we were to put some negative values in, now negative values don't really make sense in this situation. You can't have negative cubes. But you can see that if we were to do it algebraically, we'd start curving up on the other side. Okay, so there's a good example of a quadratic. So just to summarize today's lesson, basically the second differences are the values you get when you subtract the values of the first differences. So we showed you how to do that today. The curve that results from a table of values with constant second differences is called a parabola. The graphs of parabolas are symmetric, which means they are like mirror images of one another and represents things called quadratic relations. They are shaped like the letter U and maybe right side up or upside down. And I want to just emphasize one thing here. People may think, well, some of your graphs look more like V's, but notice that a V has a very definite kind of bottom to it, and then it slopes up the same. That would be a straight line. So the reason why it's not a V is that it actually is curving, and it's curving up, and it continues to curve up in that direction. So even a U isn't a very good example, really, because it does not straighten. It continues to kind of go up at an angle like that. So that's one thing to remember. Okay, your homework is page 136 and 137, number 1 and 4. I've put them on here. So which of these graphs appear to represent a quadratic relation? So think about some of the things we've said. And then it says calculate the first differences for each set of data, determine whether they're linear or nonlinear, and then calculate your second differences to see if they're quadratics. The answers to those questions are right here as well, so please just double check those. Thanks, you guys, and have a great day.